Hello, Physics 20s. In today's lesson, we're going to continue on with using Newton's second law of motion to solve problems where objects are undergoing acceleration. Although in this lesson here, we are just going to restrict the direction of motion to being in the vertical plane, perhaps just to simplify things a little bit. All we're going to do is solve two example problems, and we'll do it using the exact same procedure that we used in the previous example problem. So, first one, I have a 50 kilogram person standing on a bathroom scale in an elevator, and there's three cases described below. You have case one, elevator moving upward at a constant velocity of 3.00 meters per second. Case 2, elevator accelerating upwards at 3.00 meters per second squared. And then case 3, your elevator is accelerating downward at 3.00 meters per second squared. What we want to do is for each case, draw a free body mass acceleration diagram. And then we want to write down the equations of motion in the y direction. And then we want to determine what is the reading on the bathroom scale. Now, just before we do get started, I just want to clarify what the reading on the scale is. The reading on the bathroom scale is not necessarily the force of gravity that's acting on you. The reading on the scale is a measure of how much the scale has to push back against you to oppose that force of gravity. So the reading on the bathroom scale isn't actually a force of gravity. It's going to be the normal force the scale needs to oppose that force of gravity with. That's going to be the force that we want to calculate in this problem here. Okay, so let's break this down into our three different cases. We'll start off with case 1. I'm going to start these problems off by drawing the mass acceleration diagram first. In this problem, it tells me that, well, let's use m to represent the mass. It tells me that we're moving at a constant velocity of 3.00 meters per second. That number is just a distraction. If we're moving at a constant velocity, then our velocity is not changing. And what that means is that our acceleration is actually equal to 0 because we're moving at a constant velocity. Let's go to the free body diagram now. Now, if you have no acceleration, and we're moving at a constant velocity, that means we're in a state of dynamic equilibrium. If we're in a state of dynamic equilibrium, then our forces acting on our object are going to be balanced. So I believe here we are drawing a free body diagram of the person. And again, I'm just representing the person with a block. So we'd have two forces acting on them. We'd have the force of gravity that acts on the person, which would be straight down. However, because we're in dynamic equilibrium and the forces need to be balanced, this normal force vector should be the same length as the force of gravity vector, Fn. That's the force the scale is pushing back on us with. Now, we go to the equations of motion. Let's zoom up as positive. I'm going to find the sum of the forces in the vertical direction. Because we're in a state of dynamic equilibrium, the sum of the forces is equal to 0. Balanced forces. That's our physics principle we're applying for this part anyways. Now, we look at the free body diagram in the y direction. If the force points up, it's positive. If it points down, it's negative. So this would then be Fn minus Fg is equal to 0. Add Fg to, actually, let's expand this first. So Fn minus mg would be equal to 0. This is your expanded equation of motion. So the equation of motion is just expand as far as you can without actually manipulating the equation. When we want to calculate the reading on the scale, now we manipulate the equation. So all we need to do is add mg to both sides of the equation. You do then have Fn is equal to m times g, which would be equal to, the mass is 50.0 kilograms, multiplied by 9.81 meters per second squared, which gives me a normal force value. Just give me one moment here. I just want to pull up my key so I don't have to calculate that. And that is 491 newtons. In Newton being a kilogram times meter per second squared. Now, part B, we are accelerating upward. And again, I'm going to go to the, I should say part B, case 2. I'm going to draw the mass acceleration diagram first because it's going to help me to construct the free body diagram correctly. In this case, again, box representing the person, we're accelerating upward now. So you draw an acceleration vector that points straight up. Go to the free body diagram. Now, we have the same two forces acting on the object. We both have the normal force and the force of gravity. However, if you look at the mass acceleration diagram, if we have acceleration upwards, according to Newton's second law, you need to have a net force in that direction, which means the tug of war winner between the two forces needs to be upward. This means when I draw the FBD, the normal force needs to be longer than the force of gravity. If I wanted to, I could exaggerate that more heavily, but I think if you look at this right here, the normal force factor is bigger than the force of gravity. Your net force is up, which results in upward acceleration. To the equation of motion now, we'll assume up is positive. Find the sum of the forces. This time, because our forces are unbalanced, we accelerate. So this would be equal to mass times acceleration in the y direction. The name of the physics principle here would be unbalanced forces. Expand the equation of motion. The left-hand side is the same thing. Normal force up, it's positive. Force of gravity down, it's negative. You don't need to put down a plus in front of the normal force. I mean, it's implied that it's a positive there. That's equal to m. And we need to deal with the sign and the acceleration. Acceleration is up, so I'm going to write down a positive in front of it. We'll expand this. So we have Fn minus mg is equal to m times a. That's my expanded equation of motion for case 2. To solve for the reading on the scale, isolate the normal force variable, which we do by adding mg to both sides. So you'd have Fn is then equal to ma plus mg. I want to simplify this a little bit so I have less numbers to sub in. Just factor out a common m. And then you'd be left with a plus g. And now we can plug our numbers in. So this would be Fn is equal to 50.0 kilograms multiplied by The acceleration is 3.00 meters per second squared, plus g, which is 9.81. And that's going to give me a normal force value, which is 641 newtons. So that's the force reading on the scale. That's SI units. When you go weigh yourself on a bathroom scale, it's in pounds. Pounds is imperial units. But imperial units, personally, I don't like dealing with them. The metric system's a lot more logical from my perspective anyways. Third case. So now we're doing downward acceleration. Whoops, I forgot to write down the acronym for FBD. So let's just do that quickly up here. FBD. FBD. Case 3. FBD. MAD. Start off with the mass acceleration diagram because it's going to help us draw the FBD. Use m to represent the mass of the object. My acceleration is downward. Go to the free body diagram. Now, if you have downward acceleration, according to Newton's second law, it means that you need to have an unbalanced force down. So when we go to the free body diagram here, in order to have an unbalanced force down, the tug of war winner needs to be in the downward direction. So that means the force of gravity is going to be longer in this case here. So Fg, and then make Fn a bit shorter. If Fg is bigger than Fn, we have a net force that's down, and net force down, acceleration's down. So Newton's second law of motion is verified. Equations of motion. Zoom up as positive. Look at the sum of the forces in the vertical direction. And that's equal to mass times acceleration in the vertical direction. That's the unbalanced forces physics principle. Again, I'm not going to write that down because I've already done it. So let's expand here. Once again, Fn is up, it's positive. Fg is down, it's negative. And this would be equal to m times. In this case, though, the acceleration is down. So this is why I like to do the mass acceleration diagram, because you do need to be careful with what direction the acceleration is when you actually write one of these equations of motion. Expand it a step further, and you'd have Fn minus mg is equal to negative m times a. I'll box that. That's the expanded equation of motion. I haven't done any manipulation of the equation yet. To solve for the reading on the scale, add mg to both sides of the equation. So you have Fn. I don't want to write the negative ma term first. I prefer to write positive terms first. If we add mg to both sides of the equation, it would be positive mg first, and then subtract ma. Let's simplify this by factoring out the common m, and then be left with g subtract a. Plug the numbers into the equation. M is 50.0 kilograms. Multiply by 9.81 meters per second squared, subtract 3.00. And then Fn would be 341 newtons. I might have mentioned before that sometimes we refer to the force of gravity as being an object's weight. Although on my notes I put it in quotation marks because it's not the true definition of what weight actually is. In this case right here, what's measuring our weight is that opposing normal force. And what you can see right here is depending on how we are accelerating, whether the elevator is accelerating up, accelerating down, or moving at a constant velocity, our weight can change. So actually a normal force is a better indication as to what the weight of an object would actually be equal to. Second example, right away, you're probably overwhelmed with the amount of text that we see. This is similar to example 1 from the last lesson in that you're dealing with a system again. So a system is a collection of a bunch of objects. In this particular system, you have a pulley, a rope suspended over the pulley, and you have two masses attached to those ropes, M1 and M2. If you read the problem here, it tells me that the mass of object 2 is great enough to make the pulley rotate clockwise. So clockwise rotation would look like that. Assume negligible mass for the pulley, and there's no friction between the pulley and the connecting rope. And we'll talk again about why it's important for the pulley to have negligible mass. And then if you're taking AP physics later on, we'll come back to this and deal with a problem when you do have the pulley with mass, which does make things quite a bit more difficult. Part A. Derive an equation for the magnitude of the acceleration of the system in terms of the variables m1, m2, and g. The way we're going to do that is we're going to draw free body diagrams for both m1 and m2, write equations of motion out, and then we're going to have to solve a system of equations to figure out what the system acceleration is. B, it gives me some numerical values, and then it wants me to calculate the system acceleration and the tension in the rope, the magnitude of both of them. And then C is a bit more of a unique question, which we'll get into later, that says, using your equation from part A, identify which forces are the net force on the whole system. That'll be easier to explain when we come back to it after we do parts A and B. Part A. Let's start off with a free body diagram of these two masses. So we'll do FBD for M1. Mass acceleration diagram for M1. I'll do the MAD first because it'll help me draw the free body diagram correctly. Here you have two masses, so you do need to distinguish them. I'm going to call this one M1. And mass 1 is accelerating upward. I'm not going to call it A1 because just like in the previous problem, if we have these two masses connected to the same rope and the pulley has no mass, then we know that the acceleration of both masses is the same, and also the tension that's pulling, the magnitude of the tension that's pulling on the two masses will also be identical. Go to the FBD here. If you have upward acceleration, it means the net force needs to be up. There are two forces acting on M1. You have your weight, which would be straight down. So we'll just call this FG1. Again, because you have two masses, you do need to add a subscript to distinguish it. And in order to have a net force that's straight up, I need the applied force here to be bigger than the force of gravity. And we'll just call it FA. No need again to call it FA1 because the tension throughout the rope is the same. Let's write down our equation of motion. So we'd have, assuming up is positive, find the sum of the forces in the y direction. And we're accelerating, so this is equal to mass times acceleration in the y. Expand this. Sigma Fy would be, well, Fa points up, it's positive. Fg1 points down, it's negative. The right-hand side, we need to be more specific about the mass because we do have a system here. So we're going to say this is M1, and the acceleration is up. Therefore positive. I'll take this one step further, and then I'll get Fa. Subtract, force of gravity is just mass times the magnitude of the acceleration due to gravity, so that'd just be m1 times g, and that's equal to m1 times a. That's my fully expanded equation of motion. If you look at this equation of motion here, we cannot solve it. We don't know what FA is. We don't know what acceleration is. If you have one equation and two unknowns, there's technically an infinite number of solutions. So at this point, you can't solve the actual values. Let's go to a free body diagram for mass 2 now. And we'll start off the mass acceleration diagram because it'll be helpful in drawing the free body diagram. We're going to call this mass 2. And this mass is accelerating down once that pulley starts rotating clockwise. If we draw the free body diagram, we have the object's weight, which is straight down. We'll call it FG2. And because we have downward acceleration, we need to have the applied force smaller in magnitude than the force of gravity. So I'll draw that vector as being a little bit smaller. And we'll call that FA. Go to the equation of motion now. So assuming up is positive, let's find the sum of the forces on this object in the y direction. And because the forces are unbalanced, that's going to be equal to mass times acceleration in the y. Expand the sigma Fy part. Fa points up, therefore it's positive. Fg2 points down, it's negative. And be more specific about the mass, we're going to turn that into mass 2. And this time, you got to be careful with the acceleration. The acceleration is down, so we're going to write down a negative in front of it. Expand this one step further. So you'd have Fa minus m2g would be equal to negative m2 times a. That is my second equation of motion. Once again, you can't use this equation on its own to solve for Fa and a because you have two variables, two unknowns. But what we do have now is we have two equations and two unknown variables. So that can be solved. Now, the problem wants the acceleration in terms of m1, m2, and g. It does not want it in terms of Fa. So we need to eliminate that variable, and that's going to be the exact strategy we use to solve the system. So I'm going to write down eliminate Fa. And the way we're going to do that is we're going to take equation 1, and we're going to subtract equation 2. Let's write down these two equations, stack them on top of each other. So equation 1 is Fa minus m1g is equal to m1a. Equation 2 is Fa minus m2g is equal to negative m2 times a. Now, to subtract these, when I subtract that second equation, I need to subtract every single term in that equation. Which means, again, this negative has to go to the Fa, distributive property. It's got to go to the negative m2g, and it also has to go to the negative m2a. Now I can start subtracting in a vertical manner. So Fa minus Fa is 0. Negative m1g, subtract negative m2g. Negative times a negative is a positive, so you'd be adding m2g, and that's equal to m1a. So now we write down the terms on the right-hand side of the equal sign. Negative times a negative is a positive, so you'd be adding m2a. Now, we can simplify the equation here, and we also need to get, to solve a, we can't have it in two terms, so we're going to do some factoring. I'm just going to flip these two guys around right here because I want to write down the positive term first. So just think of it as m2g minus m1g. I can factor out a common g from that side, in which case I would then have m2 minus m1 would be equal to acceleration m1 plus m2. We've almost got our equation now. All we got to do is divide both sides of the equation by the m1 plus m2. So my system acceleration magnitude would then be g m2 minus m1 all divided by m1 plus m2. And that's my answer to part A. A lot of work to get that equation for acceleration. But the good thing is once you solve for one variable in a system of equations, it's very easy to get the other one. Part B, we're going to plug numbers in and actually calculate this now. So your acceleration would be equal to 9.81 meters per second squared multiplied by m2 is a mass of 30 kilograms. Subtract 10 kilograms. And then divide this all by m1 plus m2, so that'd be 10 kilograms plus 30 kilograms. Put everything in the bottom in its own set of brackets because you have two terms. Don't want to mess the order of operations up. And when I calculate this to two significant digits, I would get 4.9 meters per second squared. I also want to calculate the magnitude of the tension. I can do that using either equation 1 or equation 2. So that's the beautiful thing about a system of equations is that once you get the one variable, you've already done all the work to get the other one. It doesn't matter what equation you use to calculate FA, you should get the same tension value. If you don't, it means that you either calculated A incorrectly or you did the derivation wrong. So you'd have to go back to your equations of motion and double check. You might have missed a negative sign somewhere, or who knows what it could be the actual error. I'll use equation 1 to find FA. So use equation 1 to find the applied force. I'm going to take that equation, so I'll take FA minus M1G is equal to M1A. Add M1G to both sides of the equation, so that'd be FA is equal to M1A plus M1G. When I sub numbers in, I want to sub in as little numbers as I possibly can. So I'm going to simplify this one step further by factoring out the M1. And then I'd have A plus G. Let's plug the numbers in now. So FA would be equal to M1, that's that smaller mass, so 10 kilograms, multiplied by the magnitude of the acceleration, 4.9 meters per second squared, plus G, 9.81 meters per second squared. To two significant digits, we're going to have to write this in scientific notation. So in scientific notation, it would be 1.5 times 10 squared newtons. And if you want to double check that you did this correctly, I would just solve for FA in equation 2. Just plug in the acceleration value, manipulate for FA, and see if you can get the same number. C, this is where it gets a little bit weird. C says, use the equation derived in A. Okay, so let's write down that equation again. So that was the acceleration equation, which was A is equal to G m2 minus m1 over m1 plus m2. Now, on the physics 20 formula sheet, it does write down the equation for Newton's second law of motion, I believe, in terms of the acceleration. And I think it says A is equal to F net divided by M. I'm going to drop those vector signs and deal with magnitudes, and I'm going to replace F net with a symbol I like to use, which is A is equal to sigma F divided by M. We can take this equation right here and we can rewrite it for the entire system. So I'm going to write down the acceleration for SYS, the system, would be the net force acting on the system divided by the mass of the system. Now, I want to draw a comparison between these two equations. So this equation right here, we have this acceleration, which is a system acceleration. We have this system acceleration as well. We also have, because the equations are actually in the exact same format now, we have this denominator right here, m1 plus m2. Well, it turns out that is the mass of the system. The mass of the system is just m1 plus m2. So what's the net force on the system? So the net force in the system is the numerator of this equation. Let's do this in purple and kind of compare over here. Oh, I already used purple. Whoops. Let's use a different color. Whoops. What have I not used? I'll use light blue. Okay, so net force of the system would just be equal to whatever this numerator is. So let's focus on the this part right here. Let's try to figure out what forces actually make up the net force in the system. Okay, so I would have sigma F for the system is equal to G M2 minus M1. Let's expand this. This would become M2G minus M1G. What force is M2G equal to? That's the force of gravity acting on mass 2. M1G, that's the force of gravity acting on mass 1. So the net force on the entire system is the difference between the force of gravity on 2 and the force of gravity on 1. This should intuitively make sense. For example, if you got that pulley system and they both had the exact same mass, like they were both 10 kilograms, then if you went Fg2 minus Fg1, it would just be equal to 0, which tells you the net force on the system is nothing and it wouldn't accelerate at all. As long as you have a difference between those force of gravity values, then you'll have some system acceleration. And you have system acceleration because there is actually a net force on the system. Okay, so hopefully that made sense in terms of how I can take Newton's second law of motion and apply it to some more problems dealing with accelerated motion. And what you need to do is practice this on the assignment called vertical acceleration. I'll talk to you next time.